So before we go into our periodic trends, it's important to understand the forces that the proton exerts on an electron. And so let's say you have a nucleus with some amount of protons and some amount of neutrons, and you have electrons moving around the nucleus. And so if we imagine that this is one shell, which holds a maximum of 2 electrons, and so let's pretend this is 1s, and you have another set or another shell that is 2s, and so on. So let's draw another shell just for this example, and so let's just call this the 2p, and it is partially occupied. And so depending on where the electron is, it will experience a different force from the protons in the nucleus. And so it's important to distinguish the nuclear charge of an atom and the effective nuclear charge. And so the nuclear charge of an atom is represented by the letter Z, as we've seen from our last topic when we were talking about the nuclear charge of a hydrogen atom when using the Bohr equation. So the effective nuclear charge is represented by Z subscript EFF, which is, again, the effective nuclear charge. And so the difference between the nuclear charge and the effective nuclear charge is that one is independent of the electrons that you're talking about, and the effective nuclear charge is the force that the electrons experience as a result of its position in the atom as well as its neighboring electrons. And so if we look in our diagram, we see that there are some electrons that are very close to the nucleus, and there are also some electrons that are much farther away from the nucleus. And so the electrons that are much closer to the nucleus will experience more of the true nuclear charge because there are no other electrons in the way. And so if we kind of extrapolate this, so this is the nucleus and this is the electron feels the force directly from the proton onto the electron. And so this experiences the nuclear charge. But if this is the nucleus, and let's say there are a couple of electrons in the way from the lower energy orbitals, and we're looking at an electron that is farther away from the nucleus will have some kind of force on these electrons, but the force that the proton exerts on this outermost electron will be different, and so this electron is experiencing the effective nuclear charge as a result of all of the other electrons sandwiched in between that electron and the nucleus. And so these electrons are actually called shielding electrons, and the shielding effect is basically when you have electrons that are in between the nucleus and the electron of interest, and so those electrons actually weaken the force of the proton on the electrons in the outermost shells. And so we can actually calculate a numerical value for this. And so if you wanted to calculate the effective nuclear charge, this is equal to the nuclear charge minus the shielding constant. And the shielding constant is a result of the electrons that are in the way, or those that occupy the lower energy orbitals, when you're trying to understand the effective nuclear charge of electrons that are farther away from the nucleus. And so there are a couple of rules that will help us calculate the effective nuclear charge, specifically an electron in an atom. And so for Slater's rules, there are a couple of things that you need to know, and specifically we can divide the rules into two categories. And so your electrons can occupy the space in an s, p, d, or f atomic orbitals. And so there are specific rules if your electron is in sp, and there are rules when your electron is in d or f. And so if you have an electron in your s orbital and you want to figure out the effective nuclear charge for that electron, if your electrons are in the same energy level, that means that the electrons have a shielding numerical value of 0.35 in the same level. And so, for example, if you have an electron in the second energy level in the s and p atomic orbitals, that means that all of the electrons in that ring will have a shielding value of 0.35. And for electrons that are in an energy level that is 1 less than the level of interest, and so n minus 1, this has a shielding constant of 0.85. And so, for example, if you have electrons in energy level 2, when you're observing the effective nuclear charge of electrons in energy level 3, that means the electrons in energy level 2 will have a shielding contribution of 0.85. And lastly, if your electron is in some kind of lower energy, so basically if n is less than 2 or lower, that means the shielding contribution is 1. And so, for example, let's say you're observing an electron in the energy level 3, and you're trying to figure out the shielding constant for the ones in energy level 1. And so this is actually 2 levels removed from the level of interest, and so those electrons contribute a value of 1 for the shielding constant. Now, for D and F, these rules are a bit more simple, and so if your electron is in the same group, so I wanted to mention that this is different from the first case because in this case we have the same energy level, but in this case we're only talking about electrons in the actual d orbital or in F. And so these contribute 0.35, and basically everything else, so lower groups plus lower energy, will contribute 1. And so basically any electron that is in another atomic orbital, such as s or p, or electrons that are in lower energy levels, those will contribute a shielding constant of 1. And so those are the general rules when you need to figure out the effective nuclear charge. And so this will be better demonstrated by a couple of examples. So for our first problem, let's say that we need to figure out the effective nuclear charge for an electron in the 3p orbital for Cl. So whenever we figure out the effective nuclear charge, we always want to make sure that we write the electron configuration first, and then from there, this will help guide us in terms of figuring out the shielding contribution for each electron in each energy level. And so first of all, we know that chlorine is here on the periodic table, and so we can use the periodic table to figure out the electron configuration of it. And so first, we know that we can fill electrons in the first energy level, so this would be 1s2, and then from there we can fill up the electrons in the 2s orbital, and then the 2p6, and the 3s2, and finally for the p we have 5 electrons to get to chlorine, and so this would be the electron configuration for chlorine. And so let's write this out so it's a bit more neat. And so we know the electron configuration is 1s2, 2s2, 2p6, 3s2, and 3p5. And so now that we have the electron configuration, we can use Slater's rule to figure out the shielding constant, and then from there figure out the effective nuclear charge for the electron in 3p. And so for the first part, we know that electrons in the same group will have a shielding constant of 0.35. Specifically, because our electron is in the p orbital, that means that we're talking about all of the electrons in the same energy level. And so because we're talking about one electron of the 5 that we have, we know that these electrons are the ones that are contributing to the shielding. And so we have 4 from the p, and we have 2 for the s in the energy level 3. And so that means that for the same group contribution, we have 4 times 0.35 plus 2 times 0.35. And so if you plug this into our calculator, we end up with a value of 2.1. And now we need to look at n-1, which has a contribution of 0.85. And so we have 8 of these electrons, 6 from the p and 2 from the s. So we have 6 times 0.85 plus 2 times 0.85. And if we plug this into our calculator, we get a value of 6.8. And lastly, we have n-2, which has a contribution of 1, and we have 2 electrons in the 1s orbital, and so this will give us 2. If we add all of our numbers together, we get a total shielding constant of 10.9, and now we can use the equation Z effective is equal to Z minus S, and so we know that the atomic number for chlorine is 17. So this would be 17 minus 10.9, which will give you a final answer of 6.1. And so this is the effective nuclear charge for an electron in the 3p orbital for chlorine. So now let's do another example. So for our next problem, let's say you need to figure out the effective nuclear charge for an electron in a 3d orbital for zinc. So again, to do this problem, you need to first figure out the electron configuration and then order these orbitals in terms of the energy level, and then from there we can figure out the shielding contribution for each electron and then figure out the effective nuclear charge. And so if we look at our periodic table, we can spot zinc here, and so we can determine the electron configuration for zinc. So we have 1s2, sorry, I'm going to make this in a different layer. So we have 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, and 3d10. So what's interesting when you're using Slater's rule is that you actually have to group the orbitals not by the actual energy, but by the energy levels. And so we're actually going to group this, so it is 1s2, 2s2, 2p6, 3s2, 3p6, and 3d10, and 4s2. And so again, we do this because for Slater's rule, we're talking about the shielding effects when you're in the same energy level. And so in this case, we don't have to think about which atomic orbitals are higher in energy than others. And another important thing to note is that because we're looking specifically at the shielding effects of the electron in 3D, the ones that are in higher energy levels don't matter, and so we can simply ignore all of the electrons to the right of the electron in the atomic orbital of interest, and so this will not contribute to the shielding constant when we calculate it. And so now that we have the electron configuration, we can use Slater's rule to determine the shielding constant. So for this case, is a little different. So we only have contributions from the same orbital, and everything else is a contribution of 1. And so this means that we're only looking at the electrons in 3D to figure out the ones that are contributing from the same orbital. So this means that we have to do 1 less than the number of electrons that occupy the atomic orbital. So that means that we have 9 times 0.35. And if we put this in our calculator, we get a value of 3.15. And now for everything else that is outside of the orbital and lower, this means that we have to count all the electrons outside of 3D. So we have 2 plus 2 plus 6, where this is from n is equal to 1. This is n is equal to 2. And n is equal to 3. And so if we add all of these numbers together, we end up with a value of 18. And so now we can add both of these numbers together to figure out S. And so this ends up being 21.15. And if we look back at our periodic table, we see that zinc has a proton number of 30. And so the effective nuclear charge is 30 minus 21.15. And so if we plug this into our calculator, we end up with a value of 8.85, which is your effective nuclear charge. So for our last example, we have 2 parts to this question. So let's say you're trying to figure out the effective nuclear charge for an electron in lanthanum, specifically an electron in the 4f orbital and one in the 4p orbital. So in this case, we have electrons that will use different parts of the Slater rule, and so we'll be treating the electrons in each case differently in terms of determining the shielding constant. And so first, before we start, we need to, again, assign the electron configuration of lanthanum. So lanthanum is located here, and so we can first begin with trying to figure out the full electron configuration. And so we have 1s2, 2s2, 2p6, 3s2, 3p6. And in this case, since we don't need to worry about putting these in order by the actual energies of the atomic orbitals, we can just group all of the ones in the same energy level together. And so we know that in the D block specifically, the first row is 3, so I'll just write 3 here, and we know that the next one is 4, and so we know that at most we have d orbitals in the 4th energy level, and for lanthanum we know that this starts with 4, and so we can group all of these together. So continuing, we have 3d10, and we know we have 4s2, 4p6, 4d10, 4f1, and so this is the full electron configuration for this specific case. And so let me just clear this a little bit. Okay. And so this is the electron configuration, and now from there we can use this to determine the contribution of shielding that each electron has. And so let's start with the first part. And so for the first part, we're figuring out the shielding constant specifically for electron here. And so we actually know that from Slater's rule, the electrons in the same group will have a contribution of 0.35, but everything else that is in a different group or in a lower energy will actually just have a contribution of 1. And so we can actually just add all of the electrons leading up to lanthanum. And so this would be 2 plus 2 plus 6 plus 2 plus 6 plus 10 plus 2 plus 6, which simply just corresponds to the number of electrons in each atomic orbital. And so if we add these together, we end up with a value of 36. And if we look at the periodic table, the lanthanum has a proton number of 57, and so this would simply be 57 minus 36. And again, the reason why that we stop here is because everything to the right of 4F1 does not contribute because it's in a different energy level. And so this is actually not the full electron configuration because it would include things like 5s2, 5p6, 6s2. But again, for Slater's rule, we can actually ignore these because they're on a different energy level. And so going back to this, we have 57 minus 36, which gives us 21, which would be your final answer to part A. And now for part B, we're looking at the shielding effects of everything that is below and in 4p6. And so in this case, we can actually ignore everything to the right. And so we'll be working with 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s2, and 4p6. And so now we're figuring out the contribution of each electron in each of these atomic orbitals. And so if we look at the same group, we need to do one less than the value of the atomic orbital, or the highest energy atomic orbital. And so we have 5 and 2. So we can do 5 times 0.35 plus 2 times 0.35. And so if we plug this into our calculator, we get 1.75. And if we look at n is equal to 3, which is 1 less from n, these contribute 0.85, and so we have 10 electrons from the d atomic orbital, 6 from p, and lastly 2 from the s orbital. And so if we plug this into our calculator, we get a value of 15.3. And if we do n is equal to 2, or n is less than 2, these all contribute 1, and so we have 6 from 2p, we have 2 from s, 2s specifically, and lastly 2 again, but from 1s. And so if we add these all together, we end up with 10, and now we can determine s by adding all of these numbers together. And so we end up with a final shielding constant of 27.05. And so we have the atomic number of lanthanum, which is again 57. And so we can do 57 minus 27.05, which is equal to 29.95. And if we round this to 2 sig figs, this would just be 30, which is your final answer.